Okay, but what does initiation mean? How does one start a radical reaction or a halogenation reaction? Well, not surprisingly, the first step involves homolytic cleavage. Okay, so here we have molecular chlorine. Okay, and this bond is breaking to form two chlorine radicals. Okay, this takes energy. Okay, in this case, the energy is in the form of light. Okay, heat doesn't do this very well. Light is much more effective. All right, it's actually blue light, which I've sort of color-coded with the color of light here. So blue light can homolytically cleave molecular chlorine into two chlorine radicals. Okay, so these are reactive species. They're reactive intermediates. Okay, and so the way you get this reaction started is you take something that's neutral, like molecular chlorine, and you break it into two reactive intermediates or radicals. All right, so we're generating a high energy species to get this process started or initiated. Okay, we're going to come back to why reactive intermediate is important, especially the word intermediate. Okay, propagation, the continuation of this reaction. So now that we have a chlorine radical, this can abstract a hydrogen radical from methane. So we're going to halogenate methane in this overall reaction, but not in this step. Okay, so here are the arrows. So the homolytic cleavage of methane is going to occur such that a methyl radical is formed by this arrow, and then the electron that would normally just go to hydrogen is actually going to just go to form a bonding pair with the chlorine radical to give us a methyl radical and HCl, okay, hydrochloric acid. Okay, so I want to point out that in a continuation step or a propagation step, we are taking one stable covalent molecule plus a reactive radical, and we're generating another radical and a new covalent structure. Okay, so we start off with a radical, we end with a radical. And so the radical chain reaction can continue because we still have a radical that can carry the process through. The methyl radical can then react with another molecule of chlorine, okay? Because remember, this is going to happen in a flask where there's millions of these things hanging out, okay? And so again, we have a homolytic cleavage of a bond. In this case, it's the Cl-Cl bond, okay? So this electron is going over to the chlorine on the right to give us another chlorine radical. Meanwhile, these two arrows indicate single electrons pairing up to form a bonding pair. And sure enough, we get chloromethane and the chlorine, another chlorine radical. Okay, so again, we are going from one full octet or covalent structure plus one radical to a new radical and a new covalent structure. Okay, so all these propagation steps involve one radical converting to a new radical, and it just keeps going. Termination involves two radicals coming together to form a covalent species. Okay, so it can be two chlorine radicals, which I've shown here. There's all kinds of radicals flying around in a radical reaction, and when they hit each other, that step is a termination step. Okay, so if you happen to have a methyl radical and a chlorine radical come together to form chloromethane, that is also a termination step. Okay, how do you tell it's a termination step? It's because you have two radicals reacting with each other to form a stable full octet structure. Okay, so this reaction doesn't continue anymore, it just ends. Okay, now obviously if you hit this with more light, this molecule can homolytically cleave and the reaction kicks off again. Okay. Okay, so here is our summary of our monohalogenation of methane. Okay, so this is a simplified version. You can keep chlorinating the methyl group, and so you could make tetrachloromethane using this method. It's actually very hard to control. But anyway, so step one, again, you're going from a covalent stable structure to two reactive intermediates, two radicals. Okay, the propagation steps involve one covalent structure plus a radical going to a new radical and a new covalent structure, and then termination is the opposite of initiation, so you're going from two radicals to a covalent structure with the full octets. All right. So here on our BDE chart, or bond dissociation energy or enthalpy chart, I've highlighted the relevant bond dissociation values to break down this process in terms of energy. Okay, so here's a blow up and a condensing of those values. So these are all the values that we need to discuss this example in terms of actual delta H values. Okay, so we see that a chlorine-chlorine bond dissociation requires 57 kilocalories per mole. Remember that it's positive because we are breaking a bond. We have to put energy in order to have this happen. Okay, so that takes 57 kilocalories per mole. The next step involves breaking a CH bond. So on methane, we see that a CH bond costs 105 kilocalories per mole to break. Okay, but we're also forming a new hydrogen-chlorine bond in HCl, and the bond dissociation for that is 103. Okay, so we're getting 103 kilocalories per mole back. Okay, so this is almost energy equivalent, but it is slightly endothermic. All right, we're putting more energy in than we're getting out. All right. In the other propagation step, what are we doing? We're breaking a Cl-Cl bond again in another equivalent of Cl2. Okay. So in order to break that bond, it's going to cost us 57 again, plus 57. But in this case, we get a nice return on our investment. Okay, so we're forming a methyl chlorine bond. And if you look at our chart here, that's worth 84 kilocalories per mole. And since that bond is forming, we are getting that energy out or back, so the delta H is negative. And so the second step is exothermic by 27 kilocalories per mole. So if we look at both propagation steps together, the net effect is that we are getting 25 kilocalories per mole out for every time both of these things happen. All right, so the net effect of these two propagation steps is exothermic. We are getting energy out. Delta H is negative. All right, but if we look at the process to this point, we're still not getting our money's worth, so to speak. We're putting in way more energy than we are getting back because we've spent 57 up top, right here. We've spent 57 and we're only getting 25 out, okay? But you'll notice that the termination step is the reverse of the initiation step, and therefore, when you have a chlorine-chlorine termination event, or chlorine radical termination event, to be more specific, we are going to get 57 kilocalories per mole back, okay, which nullifies our initial investment. So the net effect of these four reactions is that we get 25 kilocalories per mole back every time this happens, okay? So overall, this is an exothermic process. Something I do want to talk about or point out is that the propagation step isn't just two reactions, okay? So I've shown you one example of this happening, but when you form this chlorine radical, okay, that can go off and it can react with another equivalent of methane in the reaction, okay, and then this methane can react with another equivalent of Cl2, and it just keeps going. Okay, this is why it's a chain reaction. Okay, so it's a very favorable process, and this is how we get halogenated carbons. All right, it's one of the ways we get halogenated carbons. We'll talk more about other methods later in the semester. But it's a very powerful method, and it's very useful. Okay, so hopefully this makes sense. If it doesn't, please consult me or Misun or review it in Chapter 4, and hopefully it comes together for you.